Hey there, physical science students. This is Miss Ruark. This is Vodcast 3.8. We're going to be talking about light. All right, so light. What is light? Well, light is an electromagnetic wave, and it's also a collection of small packets of energy, and we call those photons. Okay, so photons are just little particles of light. Okay, the photons are just energy. That's all they are. They have no mass, and they have no actual measurable size. Okay, so since they're energy, energy is not a form of matter. Energy is energy. In order for it to be matter, it would have to have mass and it would have to have volume. We're going to learn that when we get to the chemistry. Okay, so photons, because they are not matter, they are just energy, they have no mass and they have no measurable size, no volume. All right, so light behaves as a wave. It also behaves as a particle. Okay, so they've done observations and experiments to show that light has characteristics of waves such as interference and reflection. Okay, we've learned about those. Interference is where the two can cross over. You can have constructive or destructive, so it can amplify the light or make it go away. Okay, and then the reflection is when it's bouncing off of a surface. It's not being absorbed. All right, so other observations have shown that light is also behaves as a particle. Okay, so it can move around as a particle. It can, and one way that they've shown this is that light can actually be used to knock electrons off if it's shown on a piece of metal. It can knock electrons off of the atoms in the metal, and so it behaves as a particle. All right, so both of these models are correct. Okay, it behaves as a wave and a particle, so they call it wave-particle duality. So which model do you use? Well, that depends on which situation you're in, which situation is being observed. Okay. As far as light is concerned, it travels at the speed of light. Haha. All right, so light travels at the speed of light. The speed of light is 300 million meters per second. And that's in a vacuum, which means there's no medium, there's no air, there's nothing there to block it. Right? It's just complete and total space, empty space. All right, you can also see this now. Ooh, sorry, I'm writing with a funky mouse. You can also see that number written as 3.8 times 10. 3.8. I don't know where I got that from. Let's try that again. 3.0, sorry, times 10 to the 8th. That's where the 8 came from. Meters per second. And that's the same thing as this 300 million meters per second. It's just in a different language. Okay, in class, I remember I told y'all, you can say hello, you can say hola, you can say aloha, you can say bonjour, you can say guten tag. I think that's how you say hello. I'm not sure. Anyway, so you can say hello in all these different ways. It's still hello. Okay, so this number here, this really long number, expanded form, and this number here, scientific, they're the same number, just in a different language. All right, in air, light travels at practically the same speed because there's very small collisions with the air particles. Because it's a gas, the particles are spaced so far apart. However, when it hits another medium, such as a liquid or a solid, it's going to slow down. Okay? And when it slows down, it's going to bend. It's going to bend. Okay? A good example of when light bends, okay, light is anything that we're seeing. Okay, so a straw, if we were to take a straw and put it into a clear colorless cup of water, okay, if we were to put that straw inside of it, the light that we see is the light that's being reflected off of that straw. So when we see that straw go into the water, it looks like it's being distorted or broken. And the part at the top is going in, but it looks, if you look straight from the side, it looks like it's broken in half, and the part that's in the water is over to the side. Well, that's because when it hits that medium, the light is bending and it makes it shift. And it shows up in a different place. Okay, we're going to talk about that more in classes in the next coming days. All right, light has a wide range of wavelengths and frequencies. It depends on what wavelength that it has will affect the frequency, and thus will affect the color that you see. And since light travels with speed, c, the speed of light is equal to, you need to write this down, this equation here, the speed of light is equal to, speed of light, c, is equal to the wavelength times the frequency. The speed of light is equal to the wavelength times the frequency. You need to know that. You probably even want to write down what these little symbols mean in case you can't remember. And if you need to, pause it because I'm going to keep going. All right, C is a constant. We'd always use 3.8 times or 3.0 times 10 to the 8th or 300 million for C. Okay, so if the wavelength was to increase, so if the wavelength increases or gets bigger, then the frequency is going to get smaller. Okay, this is called a indirect proportion, okay, an indirect relationship. And if the wavelength was to get smaller, then the frequency would get bigger. Okay, indirect, which means that one does one and one does the other. Okay, I also like to refer to it as the seesaw effect because on a seesaw you have something that looks kind of like this, and one person sits on this side, and I got a really funky mouse, so I apologize, and the other person sits on this side and they push up and down, right? So when one person goes down, the other person goes up. It's the seesaw effect. They're doing the opposite. Okay, same relationship here. Remember, when frequency gets smaller, wavelength gets bigger, and vice versa. All right, light comes in different flavors, which means that you have different colors, and the colors are determined by the wavelengths and the frequencies. So if you do not have, well, you don't have these colors, and it's not written down. So I would suggest that you pause this real quick and write down the colors so that you know what they are on your notes. Okay, so it's actually Roy G. Biv backwards, and the reason why it's Roy G. Biv backwards is because high energy is on this side and low energy is on this side. Okay, now if we had switched it and put radio waves on this side and put gamma rays on this side, then it would be switched and you would do Roy G. Biv the other direction. Okay, so it all depends on the order of increasing or decreasing energy. Okay, so we've already talked a little bit about these different wavelengths and these different electromagnetic radiation that you get off of here. So just to give you a little bit more information about these, radio waves, we know that those are the longest because we talked about that in class. TV, FM, AM radio waves. Radar is an example of radio waves, and we've talked about radar a little bit when we did sound and we talked about sonar. So radar is sonar, or sonar is radar in water. Okay, so sonar is when they send out sound waves, and they detect those sound waves when they bounce off of something and they come back to tell how far away something is. Well, radar does kind of about the same thing, where it sends out a signal. Typically, it's going to be a radio wave, and it comes back, and once it comes back, they determine how long it took to get back, and then that tells the distance that the object is. Okay, microwaves. Microwaves can not only cook your food, but also be used for communication over long distances. So think space probes. Okay, microwaves can be reflected by metal very easily, and they transmit through air, glass, paper, and plastic. However, if you were to try to put them through something like water, fat, or sugar, it would absorb them, and it would get hotter, and that's how your food cooks. Okay, because the water, the fat, and the sugar absorb those microwaves. IR, infrared, we said that was heat energy, and there are IR sensors that will measure heat energy, such as your night vision goggles and your night vision scopes when you go hunting. But weather tracking can also use infrared to help determine the temperature or the infrared radiation that's coming out of a system, and it'll help determine the heat that's in a system, so they can determine the pressure, because pressure is related to heat, and they can tell if a storm system is coming or not. All right, UV, ultraviolet, most people know it comes from the sunlight. 9% of what the sunlight gives off is UV. It's absorbed in the atmosphere, in the ozone layer. And guess what? Many insects can actually see ultraviolet. That's pretty cool, isn't it? I know. All right, X-rays. We know that X-rays are used to see inside the body because they can pass through the body. Gamma rays, they can kill you. We talked about that in class. But guess what? They can not only kill you and they can cause cancer, but gamma rays can actually be used to treat cancer by killing the disease cells. Pretty neat. All right, so moving on. Color and reflection. Reflection means that all the energy is going to bounce off of a boundary. So if we're shining light at something and the light bounces back off, it's being reflected off of that object. Light's going to reflect off of a mirror, for example, because the photons are bouncing off the surface. All right, and then we have this thing called the law of reflection, which says that reflection occurs at the same angle that it originally hit the surface. So what does that mean? Well, that means that right here we have a light source that's shining this light down. Okay, it's hitting this surface, which just so happens to be a mirror, and when it hits this surface, it bounces back up. And it bounces up so that it has the same angle that it bounced and hit the surface with. Okay, well now how do we determine that angle? Well, we use this line here, and this would be called the normal. Okay, and that line is used to help us determine what the angle of reflection is, or the angle of incidence is. Okay, so what's coming in, the incoming light would be the angle of incidence, and then this would be the angle of reflection, and they need to be equal because of the law of reflection. Okay, let's see, what else we know? We see because light reflects off of objects. And color, specific wavelengths of visible light. We've already talked about that. White light is a combination of all colors. Okay, and we're going to talk about that more in the next couple days. But white light, if you take all colors and put them together, that's white light. The dark or the black is the absence of color. And then we see color because when white light hits an object, the object's going to absorb some of the wavelengths, and then it's going to reflect off some of them. Okay, everything absorbs wavelengths and everything reflects wavelengths to an extent. Okay, well, red flowers are going to appear red because they absorb all the colors, and then that should say accept, not accept. Okay, accept red, which means that it gives off that red. It does not absorb it. Okay. If we were to take a red filter, which would only allow red light to pass through, and we looked at a red rose with a stem and leaves on it, if we were to look at that red rose, the rose would look red, but the leaves and the stem and everything else that's not red would actually appear black, because it's not allowing any other color to be filtered through, to be shown through that filter, except for that red color. And we'll hopefully be able to play with some of those in class, so you'll be able to see what I'm talking about. All right, refraction. When light enters a medium, it slows down and it bends, and this is called refraction. Okay, so if the medium is shaped and it has the right curves, light will be bent at all points and come to a focus, such as the lens below, and this is the purpose of what a lens does. Okay, so it's going to take all that light and it's going to bend it in. Okay, well, let's talk about refraction. With refraction, you need to know about does it bend towards the normal or away from the normal? Okay, so if the light's coming in at a high speed and it slows down due to the medium, so it goes from high to low speed, the light will bend towards the normal. If the light is coming in at a low speed and increases its speed or speeds up after it hits the new medium, it's going to bend away from normal. And we'll practice that when you get to class. Okay, that shift is going to allow those objects to appear as if they're in different positions. Okay, that's actually what causes mirages in the atmosphere. If you're ever in a hot place and you happen to see, it looks like, they call it a mirage. Oh, look, there's a mirage. Well, it's due to reflection. We'll talk about that in class. All right, so a prism is made when white light enters a medium and each color is bent differently, and they separate into all the colors of the light. Okay, so that's what a prism is. And guess what? The Earth's atmosphere actually acts like a prism. And that's why when the sun is overhead, we see blue skies. And when the sun is not overhead, when it's setting, we see the red sky. And it's because the Earth's atmosphere is separating all of those colors, the white light from the sun, into different colors that make up that white light. And it's all based on the wavelengths and the energy that those colors have. And so you'll see when you see a beautiful sunset, you'll see all the colors of the rainbow because it separates them all into Roy G. Biv. It's absolutely beautiful. Okay, I think that covers it all, and I will see you in class.